Alright. Now then, I'm going to close the door here. You'll see, there you go. Make sure you go in here. Alright, let's get started on this thing. What we got here is we got this cylinder pressure analysis thing I put together for you guys. And what you do is you let the scope draw a pattern. And there's actually a pressure transducer that we use that we hook up to the scope. And y'all are going to be doing this. If we can get all of this other stuff out of here, we can start digging into some, you know, some of this more diagnostic learning stuff. Y'all have done a lot of nuts and bolt stuff this semester, but we need to move a little further on. All right. This is a pattern right here. Do you recognize this pattern? Have you seen it before? Anybody seen this before?
Last week.
Last week. There you go. He remembered. All right. So the primary benefits are that you can verify cam and crank synchronization, and you can check basic engine health. This is going to give you, hopefully, a deeper understanding. If you want to be able to gather data so you can repair something that's got mysterious stuff going on, there's a lot of the time you will be able to tell more about what's going on if you can actually gather some information about what's happening inside the cylinder. Now, you're only going to do this on one cylinder. Most shops are not going to have enough money to buy pressure transducers to check every cylinder. But furthermore, they do make little spark plugs that you can screw in there so the engine can be running, and you can be checking this while the engine's running. But this one here, you can pull the spark plug out. I'll show you that in a minute. We got a sensor like this one right here now. It's got a couple of bananas on it, but what we basically do, we've got an adapter that takes it down to a BNC, and it goes into our scope, and basically you're going to screw your pressure hose in there where the spark plug goes. And you can actually, on this particular one, you can use a crank signal trace if you want to, and that's not primarily what this is about. Coupled with, you can tell what the ignition timing is based on when it fires based on that TDC. Let's look a little deeper into that now. With a spark tester, when you've got that spark plug wire or whatever off of it, if you've got a spark plug wire, or if you've got a coil pack, unplug the coil pack or whatever. So put a spark plug, if it's a spark plug wire, put a spark tester in there and dial it in close, because you don't want all of that high voltage spark to be looking for somewhere else to go and go damage something. All right. So once you've got your plug out of the way, your plug out, your pressure in there, your pressure hose in there that's hooked up to your transducer. You got to have a good battery in your transducer. You know, it's got a 9-volt battery that operates it. And so you got to connect it, the signal cable, to the oscilloscope input that you're going to use. It's got to be preheated to operating temperature and idling. Right? Now there's also a snap, test you can do, but we're talking about the idling today. Measurement time should not exceed 2 to 3 minutes to keep the pressure sensor temperature below 160 degrees Fahrenheit. And that's what you're actually wanting to go be about below 70 Celsius, whenever you're thinking Celsius, I usually. All right, so we got the waveform screen. It can be numbered according to the firing order throughout the 720 degrees of engine cycle, even though you're only measuring one cylinder. All right, and so this is what you got here. There's how you do that. Now, a lot of your scopes have got a way of doing that, and the Pico scope has a way of doing it, and the little 2-trace scope that I got from Viso's got a way of doing it. That scope that came from Bulgaria. And okay, so here's your reference point. It's going to be a little difficult to see in there, but you see when your piston's going up, the pressure's going up. When it's at the top, the pressure has peaked out at TDC compression. And then when the piston's going back down, this is your exhaust valve opens right here, and then your piston's going up, pushing out on your exhaust stroke, and you see that little bit of a pressure rise right there. I sort of stretched it to make the point, but that's at 180 degrees. In other words, you're starting at the top. 180 is where on the clock? 180 degrees is 6 o'clock. Think about that. Think about starting at 0, you're at 12 o'clock. 180 is 6. 90 is 3, 6, and then 9 is 270, and then you're going to go back to 360. All right, but you got to go 2 crank revolutions to be through with an engine cycle. Got it? All right, now then. This is a continuation of that same pattern. So now here you basically have got this still going up, pushing exhaust out. Exhaust valve closes as the intake valve is opening. That right there, that little place right there is your overlap, because your exhaust valve is not quite closed when your intake valve begins to open. because the piston's close to the top, there's not a lot of space in there, but what it does is it purges the rest of that crappy exhaust gas out of there. And all that. All right, so the exhaust stroke is ended, the intake stroke's underway. That's at your 540. Oh yeah, that was nice. We had some lights go out without warning. Compression stroke again, and now you're going back to TDC. That's 720, but you could also call that reference point 0. And you're starting over, and it's going to do the same thing again. Now, when the cylinder is operating properly, pay attention to this because it's really important. When the cylinder is operating properly, pressure at point A should be approximately equal to the pressure at point B. See that? Now what's happening right here? What's this little Bart Simpson head? What's that? What's going on there? Somebody tell me. Exhaust stroke. Exhaust valve's open, piston's coming up. It has raised the pressure a little because it's pushing that exhaust out of there. And then this right here is your overlap area. Remember, this is TDC, and this is when the piston's going down, being driven down, and this is right before the exhaust valve opens, the pressure bottoms out. But that pressure and this pressure should be the same. If it's not, then that's telling you got a problem. This is fairly easy to understand when you start digging into that. You've seen this before, haven't you? You ever gone into this before? All right, the cylinder has mechanical issues like burnt valve, broken segments, camshaft timing issues. The pressure at point B will be noticeably higher than the pressure at point A because of compression leaks. See how that one there is lower than that one? When you see that, you can freeze that screen and capture the pattern just like this and analyze what's going on. And if you know what you're looking at, I'll actually put out a little booklet you guys can have to remind you of this whenever you're out there working on stuff. Most of the mechanics in this area, particularly dealership mechanics, don't ever do this. They don't use a scope very much at all at most dealerships. But your independent shops that work on everything else, they use a scope all the time. Now in this part of the country, a scope is not all that popular. But if you go to other parts of the, if you go to Atlanta or some of those places up there in Birmingham and big cities, you know, where you can make $150,000, $200,000 a year, everybody's using a scope for this stuff. I mean, people that are dead serious about fixing something without just throwing parts at it, you know, we don't want to charge somebody $500 to put a set of spark plugs in, and that happens sometimes. You know what I'm saying? Don't want to go there. So, good to know what's wrong. Okay, now look at this one here. See how that little Bart Simpson head went, instead of doing that, remember what that was? I showed you guys something like this last week. What was it? You remember? Clogged exhaust. See, because it's trying to push it out and it can't leave. Got it? All right, so the 360, 180 and 360 after the TDC, I put little degree marks there, but this silly older version of PowerPoint doesn't know what to do with that. But anyway, after the TDC compression went. So you're thinking about how far it is after that. All right, so quick rundown. There's 14 points that can be cross-referenced with either piston, travel, or valve operation. 14 points. All right, now there will be a pop test on this on next Thursday, so you make sure you know, or next Wednesday. Make sure you remember all this. You got to commit this to memory, right? You can do that, can't you? All right. Now, point 1, the cylinder pressure reaches its maximum. Got it? That first little mound, cylinder pressure reaches maximum. It's closest to the cylinder head right there. All right, point 2. After TDC 0, it changes direction and the distance between the cylinder, piston and cylinder head begins to decrease. This is going to be about 30 degrees, roughly. All right, and so that's going to be about half. It's going to be half of, this ought to be, point 2 ought to be basically halfway between here and here, and I may not have put it in exactly the right place. At point 3, the piston it continues to accelerate down until the crankshaft has passed 90 degrees after top dead center, 0. And which 90 degrees after top dead center would be the 3 o'clock position, right? All right, just before it reaches bottom dead center, the exhaust valve opens, which can be seen right here. See, when it starts going up, the exhaust valve is opened up. And if you look at the little booklet I'm going to give you, got a lot more detail and verbiage and everything on this, but basically what's in the exhaust is you got pressure in the exhaust, right? Just a little bit of pressure. Ain't much pressure, but it doesn't take much to excite this thing. All right, so section 5, that's bottom dead center, 180. I think we're at 180 degrees there. Exhaust gas enters the cylinder because the exhaust pressure is greater than the pressure in the cylinder at this point, so it starts raising the pressure up. Of course, also what keeps that pressure raised is when the piston starts going back up on your exhaust stroke. All right. Now, if the center of section 5 lies anywhere from 170 to 195 after TDC 0, the exhaust valve timing can be assumed to be correct. See anything different, you may have exhaust valve timing issues, right? This is advanced in your performance, right? This is the kind of stuff here. At this point, the pressure in the cylinder increases so it equalizes with the pressure in the exhaust manifold. That's 0.6 right here. That's the beginning of your little plateau, or your little Bart Simpson head. And you got a little turbulence in there too, and you got turbulence right here too. Once the piston has reached bottom dead center, it starts to move toward the cylinder head once again, reducing the volume of the cylinder, but now the exhaust valve's open, and so it's pushing the exhaust out. All right, it escapes into the exhaust, and between, that's 330 to 360, between 30 before TDC, the plateau of section 7 ends as the intake valve opens. And that moment the opening of the intake valve is indicated, it's going to be right in here. It's very difficult to exactly pinpoint that because you got overlap going on. Now, if you can find overlap on the companion cylinder of the cylinder in question, when both your valves are open at the same time, you found top dead center exhaust. What does that mean about the companion? It's on top dead center compression, right? That makes sense? Okay. Now then, when the piston reaches TDC 360, the exhaust valve is closed and the intake valve continues to open, so the pressure starts to equalize. Now you see these little ripples? The intake valve is opened. You got little ripples in there. The pressure in the intake manifold. Correct intake timing can be verified if the center of section 9 lies within the range of 370 to 390 after TDC 0. And this is after this first pulse. That's 370 to 390 degrees, right? And on variable valve timing, it's going to be a little different. Variable valve timing is basically changing your degrees of your camshaft on the fly. And when they first started doing that, back whenever in the mid-90s, the first recorded vehicle that did that on purpose was the Ford Contour, the Mercury Mystique. And what they would do is close the exhaust valve early so they wouldn't have to recycle any exhaust gas for each EGR. So what they did, if you close the exhaust valve early, you leave some exhaust gas in there. Makes sense. You've seen that before, haven't you? But a lot of them nowadays, they want to degree both of these camshafts so that they can actually give you more power, make it stronger. There was a guy one time that did was working on a Mustang, and he over at the Ford dealership, and he put when he put it all back together, they noticed that the fuel trims were running 10 degrees advanced on one side and 10 degrees retarded on the other. But this thing ran like a spotted ape. I mean, it would fly more than it should have, stronger than a regular Mustang. And so what they found out when they got to checking it was that he had put one of the camshafts in one tooth out, advanced. And see, if you can change it on the fly, it gives you that much more zoom. And that's what that's all about. A lot of your hot rodders will have a camshaft with degree marks on it, so they can actually change that. When they're putting it together, they'll actually, give their car a little more get up and go that way. Section 9, when the piston reaches TDC 360, the exhaust valve is closed. Intake valve continues to open, so the pressure in the cylinder starts to equalize with the pressure in the intake manifold. All right, and that's section 9 right here. And we talked about that a little earlier. Point 10, the pressure in the cylinder is equal to the pressure in the intake, and the intake valve continues to open. So you basically got that intake valve open, and you're going to see a pressure drop, because what's in the intake? As far as vacuum, right? Although there's actually pressure in the intake, but it's a lot lower. So if you've got, if you take manifold vacuum and manifold pressure, which they offset each other, like what's the manifold vacuum on a healthy engine supposed to be running at idle? 18 to 22. Well, the manifold pressure, which is what's left over, you're going to take whatever the barometer is, if it's an even 30, and you got 18 inches of vacuum, what's 30 minus 18? 12 inches of pressure, or 12 pounds of pressure actually. Inches of vacuum. You get 2 pounds of pressure per inch of vacuum. Is a sort of a screwed up deal there. I'm not going to go into the math on that. But anyway, section 11 to the second bottom dead center was 540 degrees, and this is how far the crankshaft is turned. Even though the piston is moving down, the cylinder volume is increasing, the cylinder pressure drop is not reflected in the waveform due to incoming air past the open intake valve. Okay? There's a lot of people, one of the things I was trying to do with this is condense all this. Because if you pull this kind of thing up and you start reading articles online, you can read pages and pages and pages of this stuff. And what I'm doing is I'm putting the candy where the kids can get it. You know what I mean? And trying to make it as simple and concise as I can. You know, if there'll be a little contest of stuff about people talking about, have different ideas about, you know, pressure, vacuum, all different kind of things. You know, I pretty well from the people that are really sharp on this stuff, I expect to get people sending me emails, you know, with finer points of this stuff. You know. At point 12, the intake valve is closed. And from this moment on, the cylinder pressure starts a sudden increase. That's when the piston's going back up. If the intake valve is completely closed from 560 to 600 after the previous D, you can say, I got good intake valve timing. So you can tell if the valves don't close at the right time, your pressures are going to be screwed up, right? All right, point 13, the pressure in the cylinder will be at or near atmospheric pressure, but due to the upward movement of the piston with the now closed intake valve, compression keeps going up. All right, and point 14, at 690 degrees, we're not quite at 720 yet. The cylinder pressure is approximately half the minimum pressure, you know, that's 30 degrees before. The maximum pressure, once the piston is past that position, the compression continues to increase until it reaches that. All right, do you understand that well enough to pass a test on it? You know, if you go and if you've passed all 8 of your ASEs and you want to go take advanced engine performance, if they put a scope pattern on there like this and they want to know what's going here, can you tell them? Do we need to review this? I need to give you a, yeah.
We do for real.
Yeah.
Cause I ain't gonna lie.
What I need to do is I need to print each one of you guys a little booklet that tells about this in more detail. That I've got it in a computer in here.
Wait, you already got it set up?
Huh?
You already got like
that little book?
Yeah.
Yeah, I've already got it. I mean, I've got it fixed up. I got a.
And this is advanced.
Huh?
That's advanced.
That's advanced, yeah.
That's about the only thing that I really know in the class right now.
Yeah.
Only thing I get.
Yeah. Well, anyway. All right, stop our recording here.